Welcome to the Solutions for the Modern Physics problem set for the Regents course, numbers 5 and 6. Let's go ahead and get started with number 5, reading the problem and highlighting important information. The threshold frequency of sodium is 4.4 times 10 to the 14th hertz. Our symbol for threshold frequency we know is FO. How much work must be done? How much work must be done to bring an electron to the surface of sodium? Well, what they describe in that second sentence, the work done to bring an electron to the surface of a metal, is called the work function. So they're asking us to solve for the work function given the threshold frequency. So what we start off with here, of course, is the equation for threshold frequency and how it relates to work function, and that would be phi equals HFO. The thing to note in this problem is there have been two versions of Planck's constant introduced. Unless we're told otherwise, or unless we're given electron volts in our answer, we will always use the Joule-second form of Planck's constant. So we now go ahead and we substitute the 6.63 times 10 to the negative 34 joule seconds. There's Planck's constants, that's our H value, and multiply by the threshold frequency, 4.4 times 10 to the 14th hertz. So we go ahead and we multiply those two on our calculator, and I believe we get a 2.9 times 10 to the negative 19 joules. And that's an easy enough problem. That's all they asked us for in number 5. In number 6, they extend the problem a little bit, but we're going to do it as if they did not ask us to already do number 5. It says, if light of frequency 1 times 10 to the 15th hertz falls on sodium, so what this means is this is the incident light, and if it's the incident light, that makes this frequency not the FO value, but just the F value. In the previous problem, what is the maximum kinetic energy? That would be KE max of the photoelectrons. Okay, and they also gave us up in number 5 the threshold frequency. Well, we go to our reference table, or we can go to page 4 of our note sheet, and we see that the equation that relates what we want from this, which is maximum kinetic energy, and the incident frequency and the threshold frequency, is KE max equals H times the quantity F minus FO. There are other ways to do this problem, but we're just going to use what's called the photoelectric equation to solve it. It's already solved for KE max. It looks like it would be a pretty nice, neat substitution here. This problem doesn't ask or give us any information in electron volts. It doesn't ask us for an answer in electron volts. So unless told otherwise, we'll solve it in joules. So we go ahead, KE max equals, if we're going to solve in joules, we have to use the Joule-second form, 6.63 times 10 to the negative 34 joule seconds. There's our Joule-second form of Planck's constant, times our incident frequency, 1 times 10 to the 15th hertz, minus our threshold frequency, which was given above as 4.4 times 10 to the 14th hertz. We go ahead and we subtract the 1 times 10 to the 15th hertz minus the 4.4 times 10 to the 14th hertz, then multiply by Planck's constant, and I do believe we get 3.7 times 10 to the negative 19 joules. Okay, so more thorough problem. What this is supposed to show you is that if they had given you the incident frequency, the threshold frequency, and asked you for maximum kinetic energy, that the problem is solvable all in one step. You don't have to do it in 2 separate steps. All right? All right, that'll end it for the solutions for number 5 and number 6. You'll be working on other problems in class, and we'll cover any other questions that you have.